Have you ever just looked up at the night sky and really wondered, where it all comes from? Well, today, we're going to crack open the universe's cookbook. We're going to find out exactly how it builds its most fundamental structures. So let's dive into the cosmic recipe for making a star. And we're starting inside a stellar nursery with one of the most jaw-dropping images ever taken. I mean, look at that. Thanks to the James Webb Space Telescope, we can now peer right through these massive curtains of dust and gas and see brand new stars lighting up their cosmic cradles. This, right here, is where the magic happens. But, before we start cooking, we need to know what we're actually making. A star isn't just some point of light. It's a stable, self-sustaining engine. And the key part, the thing that makes it a star, is that it generates its own energy through nuclear fusion. That's the finished product we're aiming for. Okay, so every great recipe starts with the right ingredients, right? And for a star, you can't just find these anywhere. We have to go to some of the biggest and coldest places in the entire galaxy. Welcome to the Cosmic Pantry, giant molecular clouds. Try to picture this. These are structures that can stretch for 1,000 light years, with temperatures just a few degrees above absolute zero. Unbelievably cold. And these enormous, dark reservoirs are just packed with all the raw gas and dust we need to get started. Now, check this out. This slide really shows how much is hidden right in front of us. On the left, you've got the constellation Orion, just like you'd see it in the sky. But look what happens on the right when we switch to an infrared view. Bam! Suddenly, this huge, glowing molecular cloud just appears out of nowhere. This is our stellar nursery, hiding in plain sight. So let's zoom in a little closer, right into the heart of that nursery, the Orion Nebula. Again, on the left, that's the visible light view. It's beautiful, but all that dust is like a curtain. But on the right, infrared vision just slices right through it. And look at the payoff. Thousands and thousands of young stars finally revealed. Now, these clouds aren't just big, uniform blobs. Think of them more like Russian nesting dolls. So you've got the giant cloud, right? And inside that cloud are these denser areas called clumps. And then you go even deeper inside the clumps and you find the real seeds of stars, these incredibly dense, cold pockets we call cores. This is ground zero. All right, so we've got our ingredients. They're all in place in these cores. So what kicks things off? Well, the first step in this recipe is actually a battle of epic proportions, a fight between two of the most fundamental forces in the entire universe. And here are our two combatants. On one side, you have gravity, the ultimate crusher. It's always trying to pull everything inward to make it all collapse. And on the other side, you've got pressure, the outward push from all the gas atoms bouncing around, and it's trying to do the exact opposite, to expand and resist that collapse. The entire life of a star is basically defined by this eternal tug of war. So, who wins? Well, in the super cold, super dense environment of a stellar core, the deck is completely stacked in gravity's favor. See, pressure comes from things like heat, magnetic fields, and turbulence. But because the gas is so cold, there's just not much of an outward push. So gravity gets the upper hand, and the collapse begins. So with gravity winning that first fight, the core of gas and dust starts to shrink, and it shrinks dramatically. As this whole collapse gets underway, it begins to build our baby star through a few really important steps. The whole process really unfolds in 4 key stages. First, that dense core forms. Second, gravity just takes over and triggers a really rapid collapse. Third, a spinning baby star, a protostar, forms right in the middle, and it's surrounded by this flat disk of leftover material. And finally, you get these powerful winds from the protostar that start to blast outwards. So why does that disk form? Why does it get all flat like that? It comes down to something called the conservation of angular momentum. And there's a perfect analogy for it. As that cloud collapses and gets smaller, it has to spin faster, just like a figure skater who pulls her arms in tight to speed up her spin. And that incredible spin is what flattens all the material out into a disk. So what exactly is this thing we've made? A protostar. This is the crucial middle step. It's basically a stellar embryo. It's glowing hot from the energy of its own collapse. But, and this is key, it's not hot enough in its core to start nuclear fusion yet. It's still in the process of gathering mass, getting bigger and hotter every second. You might imagine the final moments of a star's birth to be, sort of quiet and graceful. But the universe has other plans. The birth of a star is actually a surprisingly messy, chaotic, and incredibly violent affair. And you can see that chaos perfectly illustrated right here. As the protostar forms, it doesn't just pull stuff in, it also blasts these enormous jets of gas out from its poles at unbelievable speeds. We're talking hundreds of thousands of miles per hour. When those jets slam into the surrounding cloud, they create these spectacular glowing shockwaves, Herbig-Haro objects. This is a star announcing its arrival with a bang. So with all of that raw material in a place like the Orion Nebula, you would think the whole process would be pretty efficient, right? I mean, all that gas and dust. So what percentage of that giant cloud actually ends up becoming a star? Well, the answer is kind of shocking. It's just 1%. That's right, 1%. Star formation is incredibly inefficient. So what happens to the other 99%? Well, the intense radiation and the powerful stellar winds from those newborn stars are so strong that they literally just blow the rest of it away, clearing out the nursery and revealing the shiny new star cluster inside. But the story doesn't end there. All that energy blasting away the leftover gas, it isn't just waste. It can actually become the trigger for the next generation of stars. And this diagram shows exactly how that works. The energy and the shock waves from an older group of stars can basically pile into a neighboring cold cloud. That collision compresses the gas, which cranks up its density, and that gives gravity just the little push it needs to kick off a whole new wave of star formation all over again. So you see, star birth isn't just this isolated thing that happens here and there. It's a self-propagating process. It's a cosmic chain reaction. The creation of one generation of stars can literally trigger the creation of the next one, rippling through an entire galaxy over millions and millions of years. And that kind of leaves us with a final thought, doesn't it? Every single star you can see is a part of this incredible, ongoing cycle of cosmic birth, all driven by that epic battle between gravity and pressure. And it makes you wonder, somewhere out there right now, the energy from a newborn star might be compressing a cold cloud of gas, setting the stage for the next link in the chain to be forged.